That's weird. That's really weird. Think about it. Person A sees the light from the left and right hit at the same time. She watches both lights and she's like, okay, they both hit me at the same time. But person B sees them hit at different times, which is weird. Like, so the idea of things happening at the same time or different times is now different based off your perspective. And when we say perspective, we don't mean like opinions. We mean that literally in person B's world, the light are hitting that person at a different time. It's not that they see it, but it's not really happening. No, it is literally happening. The light is hitting that person at different times. Whereas person A's perspective, they hit at the exact same time. Again, this is not like a matter of opinion. It's not an optical illusion. It's not some sort of crazy trick. It actually happens at different times. And speaking of time, let's look at this. Person A sees the light travel this far. But person B saw the light start from here, but then the whole train moved. And they'll say they see it move at the speed of light, but they also see person A moving towards it. So from person B's perspective, the light only traveled this far. So the light traveled different amounts. And if delta x equals Vt, and V is the same for both person A and B, that means they have different times. Time has passed differently for these two. And again, what we're saying is that person A and person B will be will have had different amounts of time passed on their watch and biologically inside their bodies. If we're talking about light years of length for this train, and so we're taking like, oh, it took like a year to reach it from person A's perspective, it wouldn't have taken a year. Maybe it only took 6 months. So what ends up happening is person A and person B have aged different amounts by the time that light hits person A. And that is like physically, completely. They are different ages. And this has been tested. We have taken clocks, atomic clocks, and we have synced them perfect. And these atomic clocks are accurate to within 1 second every billion years. And so they take one, they put it on the spaceship, and they're zipping it around. And when they come back, they find that the time difference is specified exactly in line with the ideas of relativity in the equations that we'll get to. So this has been tested and proven. Yeah. Another point of view, let's say we have a receptor that goes up and down, and we see we have different times. The person B sees it travel, in this case, farther. What's happening is we've got, and if the speed of light's the same, we see the time's going to take different. We also have lengths changing. So person A might register the train to be 10 meters wide, but person B might only see it be 3 meters wide. The faster something moves, the thinner it gets. And not looks, it is. If you're moving very fast, you will be thinner, which is kind of fun. All right, now this is the math. Again, we're not going to be doing anything with it, but I just want to show you. This is called the gamma factor. Gamma, hey, we're using it again. Yeah, sorry. And it's equal to 1 over the square root of 1 minus v squared over c squared. And what we see is we have to start getting really, really fast before this thing starts to become a factor. So I want you to solve for gamma when v equals half the speed of light. All right.